I will need to talk about models of computation because that relates a little bit to algorithm engineering, and also I will need these models of computation later on during the computational geometry part of the course. So I will mention two theoretical models. The first one that is probably very familiar to a lot of people is the random access model. So in this model, we think of a machine as we think of computer as a machine that has two components, a CPU and a memory. So CPU has a number of registers, has some number of bits inside the registers, let's say W bits. CPU can do basic operations on the registers, such as you can add, subtract, multiply, compare, if statements, you can do branching instruction, etc. Just think of any of the basic operations that you can do in C or C++ or something like that. And on top of that, you can also read and write memory. You can have addressing, you can address, let's say, an array, you can get the ith element of an array, all of these things. You can do all of these things in constant time. So this is known as the random access model. And obviously W is a parameter in this model, and for example in a modern computer you can think of input, if you have a bunch of long integers you can think of W as 64 bits, etc., etc. When it comes to computational geometry though, and then this model makes a lot of sense because let me just go back to the quicksort example that I had before. So think let's say this quicksort pseudocode. It is, we have a quicksort function that calls the partition function to partition the array into two low and high using a pivot, and then you recurse using the then you recurse by calling quicksort again. And the partition is essentially a loop that you go from both sides of the array, and then you try to essentially organize it such that the left half is smaller than the pivot, right half is larger than the pivot. Okay, so that's a very basic implementation of quicksort. You could implement this using, let's say, C or C++, and let's say this could be one piece of the implementation. So you get the pseudocode and then you turn it into a C++ code like this. Okay, so this actually compiles. I copy pasted somewhere from internet, and then you compile this and you get some kind of machine code for this. So for example, the machine code of your partition step could be something like this. Okay, and it is true that every basic operation that he had in the pseudocode has been translated to a constant number of machine operations. So obviously, once I look at the machine code, there are lots of instructions here. But it is true that every single step of this partition algorithm, every basic step of the partition algorithm has been translated to a constant number of machine instructions. We can assume that all machine instructions take roughly the same time. I mean, obviously some machine instructions are faster than the others, but if you're ignoring constant factors, then they all take constant time. And since every step of every instruction in the pseudocode takes constant time, this assumption is kind of justified, that I can assume that my pseudocode translates into every statement in the pseudocode translates a constant number of instructions that take constant amount of time. So therefore, I can just assume that I'm writing a pseudocode that takes a constant amount of time per operation. Okay. So this, from a theoretical point of view, this model actually makes a lot of sense. When it comes to computational geometry, because of some technical issues that I'm going to talk about, we expand this model to be a model that is called realRAM. This model is a little bit crazy. So a realRAM is a random access machine that is equipped with real registers. So on top of the integer registers that are like normal registers of any normal modern computer, this machine, this theoretical machine, has real registers that can store any real number up to infinite precision. And on top of that, it can do basic arithmetic operations, including the kth root of a real register. And it can do all of these things in constant time up to infinite precision. So for example, if you want to compute square root of 2, you can just compute that up to infinite precision in constant time. You cannot compute pi, for example, because you cannot compute pi using repeated squaring. Okay? So it has some limitations, but it looks like it is actually a crazy model. And why is it that people study this model? Okay, I will talk about why people study realRAM in the next video.